Okay guys, so this last video is going to be over proving continuity. There's 3 steps when we prove continuity. The first is, in order for a function to be continuous, it must satisfy the following criteria, okay? So f of a must exist. So there must be a solid point. Now we're not going to say a solid point exists, we're going to say f of a exists because we have to use math terminology. The limit as x approaches a must exist. Okay, that means that the left-hand limit has to equal the right-hand limit. And step 1 and 2 have to equal each other for it to be continuous. Okay, so what we're going to do is we're going to graph the piecewise function and then we are going to prove the continuity. So graphing piecewise functions, we should know how to do that from the last lesson. Okay, so we're going to go through and we're starting at 1. We're going to pick values less than 1. Okay, so plugging in 1. 1 minus 4 is a negative 3. 0 minus 4 is a negative 4, negative 5, negative 6, and negative 7. Okay, and then y is equal to 3x. And we're going to go for points greater than 1, so we're going to do 1, 2, 3, and 4. Okay, now this is going to be a closed point here, and this is going to be open. And so we're going to go to graph this. 1, negative 3 is down here. 1, 2, 3. It's going to be closed. 0, negative 4 is down here, and we're going to go down 1 over 1, all of those, and we're just going to get an idea of what the graph looks like. So we're going to use our straight edge again. And that branch looks like that. Now the line y is equal to 3x. We're going to start at the point 1, 3, 1, 2, 3. It's going to be open. Up 3 over 1, 1, 2, 3, 1, 2, 3. So it's going to look something like that. And our graph looks like that. So we can prove continuity from a graph, or we can prove it just using the piecewise functions. Okay. So our first step is f of a must exist. So f of 1. So we usually prove continuity at the points over here. So whatever your boundaries are. So f of 1. 1 minus 4 is equal to a negative 3. Okay? Second step. The limit as x approaches 1 from the negative side. And we do the limit as x approaches 1 from the positive side. Okay, as we come from the left-hand side, your limit should be a negative 3. As I come from the right-hand side, you can either use your graph or use your chart is equal to 3. Okay. Now, since the limits aren't equal to each other, it does not exist. Okay, so once one step is violated, it's not going to be continuous. So you say, since the limit as x approaches 1 of f of x does not exist, therefore not continuous, at x is equal to 1. Something like that. Your statement has to look something like that. Now, you can tell that in order for something to be continuous, there must be no breaks or jumps in the graph. Okay? So as you can see, there's a big jump in the graph, and that's why the limit doesn't exist. If your fingers were to line up, then the limit would end up existing. Okay? So, let's go on to the next example. We are going to go at 0. So we get y is equal to x plus 4. And we're going to start at 0. So 0, negative 1, negative 2, negative 3, and negative 4. 0 plus 4 is 4. Negative 1 plus 4 is 3, 2, 1, and 0. Okay? And then I have y is equal to 2x plus 4. And I'm going to pick values greater than 0, so 0, 1, 2, 3, and 4. 6, 8, 10, and 12. So when we go to graph these, this is going to be closed in this branch, and it'll be open in this branch over here. So when we go to do this, x plus 4, so let's graph the first one, start at 4, 1, 2, 3, 4. And I'm going to keep going down like this. And our graph looks like that for that branch. Now, the next one, we're going to start at 0, 4, and it's going to be open. Now, once one point is closed, colored in, it stays colored in. It doesn't matter if one is open, one are closed. It's going to be solid. Okay, so we're going to start at 0, 4 and 1, 6. Up 2 over 1, up 2 over 1, like that. So our graph is going to look like that. Now, so we can tell that there's no jump in the graph, okay? So our first step, we're going to prove the continuity at 0. So f of 0 is equal to 4, because the equal to branch, we're going to plug in a 0. 0 plus 4 gives you 4. We're going to do the limit from both sides. Limit as x approaches 0 from the left-hand side, and the limit as x approaches 0 from the right-hand side, okay? So the limit as x approaches 0 from the left-hand side should be 4. The limit as x approaches 0 from the right-hand side should be 4. So therefore, the limit as x approaches 0 of f of x is equal to 4. Oop, sorry. Ran off the paper and I hit my camera. Is equal to 4, sorry. Okay, now, since step 1 equals step 2, so we say, since f of 0 equals the limit as x approaches 0 of f of x, therefore, continuous at x is equal to 0. And you can tell that there's no holes or breaks in the graph from what we did. Now, you're not going to have to graph this most likely on an AP exam, but it's good to know how to graph piecewise functions and what we're looking at them, okay? So on the next one, it says evaluate the following given the piecewise functions, and we're not going to graph on this one. So f of 1 lies in the top branch because it's equal to branch. So 3 times 1 is 3 minus 2 is 1. F of 0 also lies in the top branch, so it comes out to be negative 2. F of negative 1 also lies in the top branch. So negative 3 minus 2 is a negative 5. And then 6 lies in the bottom branch. So 6 plus 2 is 8. Now it says I want to prove the continuity of the function at x is equal to 1. So our steps are f of 1 is equal to, well, it's in this branch, we already found it, is 1. Now I'm going to do the limit as x approaches 1 from the left-hand branch and then the right-hand branch. Okay, so the limit as x approaches 1 from the left-hand side, I'm plugging into this branch, the left-hand branch, so I get a 1. As I plug into the right-hand branch, I get a 3. So, once we get your left-hand limit and your right-hand limit, they're not equal to each other. So the limit as x approaches 1 of f of x does not exist. And since that limit does not exist, therefore, not continuous at x is equal to 1. Okay? So once it violates one of the steps, it is not continuous. Okay, we've got 2 examples left. Okay, so we're going to prove the continuity of x is equal to 0 for this one. So y is equal to x squared, and we're going to pick values less than 0. Okay, so we're going to start at 0, 0, -1, -2, -3. Okay, so if I plug in a 0, you get a 0. Plug in -1, you get 1. Plug in a -2, you get 4. Plug in -3, you get 9. Okay, it's going to be open at 0, 0. And then I'm going to use y is equal to x. And I'm going to plug in points greater than 0. Okay, so we get 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. This is going to be closed. Okay, so it's closed right there. So we're going to have a parabola and a straight line. So we're going to plot the point 0, 0. It's going to be open. -1, 1. 2, 4, 1, 2, 3, 4. And 3, 9 is up here. So it looks like that. And then we got the point 0, 0, 1, 1, 2, 2, 3, 3. Now, 0, 0 is going to be closed in right here. It was open right here, so I'm going to go ahead and color it in. Okay, and I'm going to draw my line. So that's what my graph looks like. We got a parabola and a line. So we're going to do f of 0. F of 0 is going to be equal to 0. We're going to do the limit as x approaches 0 from both sides. Okay, so the limit as x approaches 0. As I come from the left-hand side, your y value is 0. Okay, so I get that from plugging into the top branch. The bottom branch is the right-hand branch. The y value is also 0. And so the limit as x approaches 0 of f of x is equal to 0. Okay, now we say since f of 0 is equal to the limit as x approaches 0 of f of x, therefore continuous at x is equal to 0. Okay, and then let's do on the next one, let's prove the continuity at x is equal to a negative, let's do a negative 2. Let's do a proof continuity at x is equal to -2. Okay, so we're going to graph these lines. Y is equal to x minus 1. Okay, so I'm going to pick values less than -2. So I get -2, -3, -4, and -5. So I'll plug in a -2. -2 minus 1 is a -3, -4, -5, and -6. This is going to be a closed point because it's equal to. The next branch we're going to do is y is equal to 2x minus 1. And we are going to plug in points in between -2 and 4. Okay, so -2 times 2 is a -4, minus 1 is a -3. -1 times 2 is a -2 minus 1. Whoa, wait, hold up. Sorry, -5. That should be -5, -5. Okay, -1 times 2 is a -3 minus 1 is a -3. -1, 1, 3, 5, and 7. And then the last branch, we'll do y is equal to negative 3x plus 8. Okay, so negative 3x plus 8. So I'm going to pick values greater than 4, 4, 5, 6, and 7. So is a negative 12 plus 8 is a negative 4. 5 times a negative 3 is a negative 15. A negative 15 plus 8 is a negative 7. Plus a 6 is a negative 10. And then the rest will be off. So that's what we get. Now, we need to do our open and close points for this. So this is going to be open, and this is going to be closed. And this is going to be open right here. Now, from there, we are going to graph these. So x is greater than, so we'll do this one first, negative 2, negative 3. It's closed. Okay. 2x minus 1. We're going to graph that for these points right here, negative 2, negative 5. 3, 4, 5. It's going to be open right there. And I'm going to go to the point 4, 7. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. It's going to be closed. So I'm just going to connect the dots between those 2 points. You can plot all the points in between if you want to. So it looks like that. And then I have 4, negative 4. 1, 2, 3, 4, 1, 2. It's going to be open. 5, negative 7. So it's going to be 1, 2, 3. So it looks like that. So your graph looks like that. So I want to prove the continuity at x is equal to a negative 2. Okay, so just say it'd either be negative 2 or 4 usually. Okay, so at x is equal to negative 2, f of negative 2 is equal to a negative 3. Okay, we get that from our equal to branch and it's colored in. The limit as x approaches negative 2 of f of x from the left-hand side, and we're going to do limit as x approaches negative 2 from the right-hand side. Okay, so the limit as x approaches negative 2 from the left-hand side is a negative 3. The limit as x approaches negative 2 from the positive side is a negative 5. And so they're not equal to each other, so the limit as x approaches negative 2 of f of x does not exist. Since the limit does not exist, therefore not continuous at x is equal to a negative 2. Okay, so this has been an introduction to continuity. Make sure you go through your 3 steps. F of a must exist, the limit as x approaches a must exist, and they have to equal each other for the function to be continuous. Okay, thanks and have a good day.